Oh, so we meet again. Oh, you come to this class on time, do you? Interesting. Is Dr. Skimbortis more scary than I am? Is that what it is? How dare you be here on time? How dare you? Let's see here. Oh. You'll come later? No. You just come on time tomorrow instead. How about that? All right. I'll begin with a verse of Scripture. This is Colossians chapter 1, verse 15. He is the image of the invisible God, the firstborn of all creation. For by him all things were created, both in the heavens and on earth, visible and invisible, whether thrones or dominions, or rulers or authority, all things have been created through him and for him. He is before all things, and in him all things hold together. This is Colossians 1, 15 through 17. So, I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, I thank you for this class. We just pray for Dr. Skimbortis that he would be able to get back here soon. And in the meantime, help me to do a good job in his absence. Lord, in the end of my prayer, Lord Jesus. Amen. All right, so let's talk about row reduction. So you guys know how row reduction works, right? How's it go? You have an elementary matrix A, right? I mean, you have a matrix A, right? We'll keep it real. Let's say in our, this is my notation, guys, just so you're used to me. This is an m by n matrix with real coefficients. And then what do we do? You take A, right? And you go to maybe the first reduction, which you could say an elementary matrix, right, times A. That's like the first row reduced version, right? And then you do another row operation, right? And then that's like E2 times the previous one, right? Which we could call R2, right? And this goes on, right? For a while. Eventually, after K, let's say, row operations, so we've got EK minus 1, dot, 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 E2, E1 times A, we get to the what? The reduced row echelon form of A, right? And that, in a nutshell, is Gaussian elimination, right? The Gauss-Jordan elimination. We do elementary row operations. We take a matrix, and after K elementary row operations, we attain the reduced row echelon form of the matrix, which is what? It's unique, right? Do you guys know how to do this? Yes? I think. All right, so let's see here. Let us do an example of that so we can reference it in what follows. All right, so let's make this matrix big enough. Something like, oh, I don't know. 1 minus 2 minus 4. I don't know. 3, 3, 3. 4, 1, minus 1. 2, 5, 7. 7, 4. Where was I? Uh-oh. 2, I think. All right. And then for good measure, we'll throw in a 1, 0, 0. All right, great. All right, so this is a what? This is a, a 3 by 6 matrix, right? Okay, great. Let's row reduce this thing. So first order of business, I will take row 2 plus 2 row 1, and I'll take row 3 plus 4 row 1. All right? So that means nothing happens to row 1, so let's just write that down again. 1, 3, 4, 2, 7, 1. probably going to regret my choice of font size here. Maybe it's not as bad as I think. I don't know. All right, so I've modified the second two rows. So what you got? Well, we swept out here. We've got 0 and 0 there, right? So I said row 2 plus 2 row 1, so that makes a 9. Row 2 plus 2 row 1, 9. Row 2 plus 2 row 1, 9? What? Is that right? Row 2 plus 2 row 1. Ah, phew, finally. All right, there we go. And then row 2 plus 2, 2? Okay, cool. And then what's next? Let's see, row 3 plus 4 row 1, so we got 0. Row 3 plus 4 row 1, so that's 3 plus 12, which is 15. Minus 1 plus 16 is 15. Hey, what? 7 plus 8, 15. That's weird. All right. What we got? Row 3 plus 4, row 3 plus 4 row 1, 28 plus 2, 30. Huh. And then what we got here? 4? All right, great. Let us move on. Next up, I would suggest we... Ew. Really? Oh, man. How'd that happen? Okay. I'm going to divide by 9. Row 2 over 9. I hate fractions. Okay? So that's going to give us a 1, 3, 4, 2, 7, 1. I know this takes some time, but we need this example to bring the other things I'm going to say today to life. 1, 1, 1, 2. And, fraction. 2/9. Hate fractions. 0, 15, 15, 15. If I make a mistake, I would like to know about it, like, immediately. Are there mistakes here? Okay, cool. All right, so then I'm going to go ahead and clear out the 15 there. And I think, yeah, I guess I'll just clear the 15 out, see how that goes. So row 3 minus 15, row 2, what's that give us? So the top 2 rows are unaltered. Still got our 1, 3, 4, 2, 7, 1. And my 0, 1, 1, 1, 2, 2/9. The altered row here, 0, 0. And all right, so 0. And what's that? 30 minus 2 times 15 is 0. All right. And then what? I'm 1 behind. Oh, so I there we go. Thank you. So it's, oh yeah, 0, 0, 0. Okay, good. And then, yeah. What is 4 minus 15? You know what? You know what? It doesn't matter, right? Because let me just get to the point here. What happens after some row reductions? This will be 1, and these will be 0, right? So let me just erase that and say row equivalent. There you go. Okay. You're like, that has served me well on tests. So you're allowed, right? Okay. Are we done? Not quite. One more step, right? One more step. We can do row 1 minus 3 row 2, right? So I think, does Anton talk about the forward and the backwards pass? Have you guys read that part of the book? Nah, okay. Does Lay talk about that? I'm teaching out of Lay, I should know. I'm not ready to read Lay. Don't tell my students. Let's see here, so 0, let's see here, 1, so I do 4 minus 3, which is 1, 2 minus 3, which is minus 1, 7 minus 6, which is 1, and that's still 0. Then this one's unaltered, 1, 1, 1, 2, 0. And then finally, last but not least, well actually it is least, isn't it? 0, 0, 0, 0, 1. All right, behold, this is the reduced row echelon form of A, our beloved, unique, ultimately reduced matrix, right? So I don't know what you guys were taught in 221. I'm curious. Can you tell me anything about A as it relates to the reduced row echelon form? Okay, oh yeah, so if we, well, okay, so you're,
This is augmented, yeah.
oh yeah, sure. So if, I will grant that. If we had A was equal to like A, let's say A1 concatenated with B, right? For like A1x equals to B, totally on board with you. That's an inconsistent system on the on the basis of the last row. Absolutely. Can you guys tell me anything else?
There's a lot of free variables.
There's going to be a lot of free variables in the solution. Great. Anything else?
It's column span R3.
It's column span R3. This is true. Okay. Can you tell me anything else like relating A in the reduced row echelon form of A? Same solution set. That is true. Every time we do a row, we find row equivalent matrices, we are trading the system of equations represented by the original augmented coefficient matrix for a new system with a new augmented coefficient matrix, which has the same solution set, right? So that's the row equivalence of augmented matrices is one and the same as saying we're not altering the solution set to the system. Absolutely true. Yep. Anything else? It's rectangular, so inverse doesn't make sense. Throw you a bone. Okay, let's prove something. So, let's do a calculation. This calculation will lead to a theorem. And so, let's let A, let our EF of A, actually I don't even need to do that. Let me, well, I'll prove it for this, and then we'll. I'm going to prove it for this, and then I'll dial it back and show you it does a little more than this. But let's let the reduced row echelon form equal to E times A, right? That's possible because this is what? The product of what? Elementary matrices, right? You remember that? You guys talk about that in 221?
Yeah.
Not at all? You guys don't know what an elementary matrix is whatsoever? Nobody? So you guys aren't sure. So, for instance, if we were to take the matrix, like this first row, let's do this one right here. Row 1 minus 3R row 2. If I take the 3, take the 3 by 3 matrix, I think. Let me think. Yeah, 3 by 3 matrix. I take the identity, right? 1, 1, 1. All right. I take the identity matrix and I do this to it. So row 1 minus 3 row 2. So what would that do? Put a minus 3 right here, right? Row 1 minus 3 row 2. So this is the identity matrix with that row operation, all right? Okay? This you can call, the notation I use in the notes I've written, would be something like this, R1 minus 3R2. So it's the elementary matrix that corresponds to that elementary row operation. Here's the thing. If I call this thing R42, just to give it a name, then this right here, you can calculate, is nothing more than R1 minus 3R2 times R42. Every row operation can be implemented by multiplication by an appropriate elementary matrix. An elementary matrix is simply one where you take the identity and you do an elementary row operation to it. That's it. Try it out. Does that work? Can you guys see it? If I do this times that, what happens? Does that even make sense? Three by 3 times 3 by 6. Yeah, it's okay. This product makes sense, right? 3 by 3 times 3 by 6 gives a 3 by 6. Great. I'm just having trouble visualizing it because I've wrote it here and I'm tempted to put it here, but it should go over here. So anyway, the 1 gives you 1, 0, 0. This one gives us 0. I'd have to write it out, but if you write it out, you can see that multiplying this by that on the left gives you that. All right. And so there is a matrix like that for every single, like I'm writing up here. So apparently I was just writing gibberish for you guys at the start of class because you don't know what I'm talking about, right? I'm talking about these specific matrices, elementary matrices. They are invertible and they are easy to obtain by the operations that correspond to the elementary row operations, just that, okay? And it's totally understandable that your 221 professor didn't emphasize this because they're not that calculationally useful. But theoretically, they're very useful. So the product of elementary matrices E, the beautiful thing about it is every elementary matrix has an inverse. What's the inverse? Oh, thanks, Jeff. The inverse is just to do the opposite row operation, right? Instead of, thank you. Instead of, like this one, the inverse of this would just be R1 plus 3R2. Check it out. If you multiply 1 minus 3, 0, 0, 1, 0, oh man, I just realized what Jeff did. 1, 3, 0, 0, 1, 0, 0, 0, 1. I think I'm out of frame. Check it out. That is the identity. Thanks, Jeff. It's gotten kind of persnickety because the stupid adapter thing pops out. Does that work? If you guys can see it. I'm sorry those of you who have foolishly chose to sit behind the lectern. Should have brought a periscope or something, I guess. Does it work? All right, so trust me when I tell you every elementary matrix is invertible. All right, and can you guys tell me the product of invertible matrices? Invertible matrices is what? Is again invertible, right? So that means that this matrix E is an invertible matrix. Whether or not A is invertible, E is invertible. All right? Great. So that's the starting point. Now let us suppose that let's call this thing R. All right? R. Suppose that column J of R is equal to a sum I equals 1 to n of Ci column I of R. All right? So what am I saying? Oh no, just put it into words. What am I saying? I'm saying that the jth column of R is actually a what? It's a linear combination of the other columns of R, right? This could be very stupid. It could just be column J of R is equal to 1 times column J of R. That's like a case of this, but it's more interesting if there's an interesting linear dependence, right, amongst the columns of R. Yeah.
Wouldn't you have to assume I is not equal to j for that to be in use?
No, not at all. So, but it's most often interesting when I is not equal to j, but we can just make that coefficient 0. No, it's fine. Don't worry, I'm not going to divide by c sub j, so we'll be okay. Anyway, so then take this equation, multiply by e, what happens? Then that gives us e column j of R is equal to, and I'm just going to, jump to the point here. What happens when we multiply a matrix times a sum? I guess I'll write a step. So you guys know properties of matrix multiplication, right? So like if I have matrix times the sum of vectors here like this, what can I do by properties of matrix multiplication? I can pull the constants out, and I can pull the summation out. I can rewrite this as the sum I equals 1 to n of ci times e coli of R. This calculation's sick. All right. Oh, that's just an accident, isn't it? Not like I'd choose this notation just to make a stupid joke. That would never happen. So, what is this, though? I guess I need to talk to you guys about something. You may or may not know about this as well. So if I have E times A, right? I can also look at that as E times column 1 of A times column 2 of A. Column, how many columns does A have? I think we said n, right? And one of the things that's true about matrix multiplication is that you can go column by column, right? An identity for matrix multiplication is that in the product of EA, you can rewrite as E column 1 of A, E column 2 of A, E column n of A, right? And by the way, this is equal to R. Right? So this is equal to, if you allow me this short manga style calculation, like column 1 of R, column n of R. Ha, I fit it in. Woohoo. What does this mean? What's the relation between the columns of R and the columns of E, columns of A, and this E matrix? It's very simple, right? If you look at this, and you look at that, you can see from this that column, let's say J of R is equal to, maybe I should say I. Column I of R is equal to what? It's equal to E times column I of A. Do you guys see that? Because those two matrices have to be equal column by column if they're equal. So that's how the columns match up. So what does that make this? And what does that make that? See what this says actually then? So like, let me take this and this and use this relation right here. What does that give us? We get that column J of, oh man. Shnikes. Rats. Well, that's not what I want at all. Like, we're just going to go back where we started if I'm not careful, aren't we? Wait a minute. Oh man, what have I done? Give me a second here. I'm too close to it. Oh, phooey. I should have started with the linear combination not in R, but in what? All right, there's two ways to fix this. The one is to change my E's to E inverse. The other is to change my original linear combination. Instead of having R's to have A's, I think that's the easier modification. So let's do that. I'll make the correction in orange. So sorry, guys. So what I should have supposed is just to put an A here and put an A here, all right? If I do that, nothing changes about the upper calculation. All that changes is this puts an A here, and it puts an A here, and it puts an A here. All right, now we can meaningfully apply the double underlined formula, right? So what does that give us? Column J of, what we got? Column J of, how's it go? Column J of, not A, but see that? I can trade an equal I for a column I of R. So I can trade an equal J of A for a column J of R. And that's equal to a sum, I equals 1 to n, of Ci column I of R. This argument can be reversed as well, right? Like you could start with what I boxed, and if you were to multiply this by the inverse, E inverse, you could just as well go to the other, go back. So in other words, what I have boxed is true if and only if what I'm about to box is also true. Like these are interchangeable. If you have one, you have the other. If you have the other, you have the one. In fact, I really could say more, right? Because I'm assuming it's the reduced or echelon form just to make it concrete. But really, I could just as well have done this for any row equivalent matrix to A, right? So what theorem have I proved? What does this calculation prove? Theorem. If there exists a linear dependence amongst the columns of A, then there exists the same linear dependence amongst the columns of any row equivalent matrix. This I refer to as the CCP. For me, this is the column correspondence property. Now, it's probably called the linear correspondence in Anton, if it's named at all. The undergraduate linear algebra book that I learned linear algebra from did not have this. And it fundamentally handicapped me for my graduate linear algebra class. Because this is an incredible tool for the questions we're about to ask and answer. This replaces running logic through systems of equations with simple pattern matching. Why? See, the thing I asked you, I was trying to see if any of you knew, is that whatever patterns that you can see in my row-reduced matrix, those are also evident in every single matrix up to that reduction. Did you know that? With the pivot columns. But between any of the columns, any linear dependence you can see. Let's go back. Let's look at it. Let's see if I'm right. So part of the beauty of the row-reduced echelon form is that the pivot columns are the standard basis, right? The pivot columns will be E1, E2, ... ek, where k is the so-called rank of the matrix, k being the number of pivot columns, all right? So, yeah, pivot columns for this one were what? This guy, this one and that one, right? Those are the pivots. The structure of the reduced row echelon form of a matrix, it will always be the case. Sorry about that. That the non-pivot columns can be built from the pivot columns. The ones that actually are to the left of that non-pivot column, right? So like row 3 is what? It's nothing more than, excuse me, row 3, listen to me. Column 3 is what? It is the sum of columns 1 and columns 2. It's obviously true for the reduced row echelon form, but it's also true everywhere before if you just look at it. 1 plus 3 is 4. 0 plus 1 is 1. 0 plus 0 is 0. 1 plus 3 is 4. 0 plus 1 is 1. 0 plus 15 is 15. 1 plus 3 is 4. Minus 2 plus 3 is 1. Minus 4 plus 3 is minus 1. 1 plus 3 is 4. 0 plus 9 is 9. 0 plus 15 is 15. Everywhere. Always the pattern. Let's go to row 1, 2, 3, 4, 5. Row 5 is row 5. Listen to me. Column 5 is column 1 plus 2 times column 2, right? That is always the case. Check it out. Column 5 is column 1 plus 2 times column 2. 1 plus 6, 7. Minus 2 plus 6, 4. Minus 4 plus 6, 2. How do I know this? It's how I made the matrix up. Right? But you didn't know this, did you? Did you know this? Maybe. Maybe not. It's not emphasized in a lot of books, but once you understand it, you can answer a number of interesting questions without actually thinking about systems of equations. You can just use this theorem directly. Let me show you what I'm talking about. So, definition. The column space of A is the span of the columns of A. So here, I'm sticking with my assumption that A is an M by N. M as in mommy, N as in nanu nanu. It's a Mork and Mindy reference if you're wondering. I know you weren't. But that's from like, well, it's pretty much from when I was a toddler. I've not really seen it. It's probably full of all sorts of objectionable alien humor. Who knows? Anyway, the column space is the span of the columns, right? This is itself a subspace of what? Each column is column vectors of what? It's a how many dimensional vector? It is an m dimensional vector, right? So this is a subspace of Rm, right? In my notation, Rm is equal to Rm by 1. The m by 1 matrices. Yep.
What does it mean for a set to be less than or equal to a set?
That notation means that the column space is a subspace. There are two important subspace theorems, right? The one is that you can apply the one-step or two-step subspace test, right? To show that this set is a subset of the given vector space and that it's closed under addition and scalar multiplication, right? If you show those two things, it's a subspace, right? I think you guys learned that. The other theorem, which is ever so useful, is that span is a subspace. If you can write a set as a span, game over, subspace. This is the span subspace theorem. It's not celebrated enough because it's amazingly simple. But it is a fact that a linear combination of linear combinations is once more a linear combination, and that proves that the span is a subspace. Because if you add two linear combinations together, you get a linear combination. And if you scalar multiply a linear combination, you get a linear combination. Therefore, span is a subspace. Yeah?
Nothing. You answered my question.
Oh, okay. Cool. So that's the column space. All right. Furthermore, the dimension of column space is equal to the rank of A. The rank of A is the dimension of column space. All right, another important space is null space. The null space of A. This is X in Rn such that Ax equals to 0. In other words, the null space of A is the solution set of the homogeneous equation. So it's always non-empty, right? It's always got 0 in it. And it's very easy to prove that this is a subspace by the subspace test theorem. Because if you have two homogeneous solutions, the sum of homogeneous solutions is again a homogeneous solution, and the scalar multiple of a homogeneous solution is again a homogeneous solution. Work it out for yourself if you don't believe me. Prove for yourself that the null space is a subspace. That's definitely like I'd say it's a good test question, but it's kind of too simple. I mean, a test should be harder than that. You're like, shut up. All right, so Rn, don't worry, Dr. Scambordis will not listen to me. So n cross 1. Yeah.
So the null space of A is the set of homogeneous solutions?
That's right. Yeah, yeah. So that's the null space. Now, the dimension of the null space has a name. It's called the nullity of A. And sometimes this is abbreviated like RK of A. Sometimes this is abbreviated like nu of A for nullity. What'd I say? Did I miss something, or?
No, I was just asking her what she had asked you.
Oh, cool, cool. This is your class, guys. So like, you stop me, ask questions. It's cool, you know. All right, so we've got two subspaces, right? Column space of A, the null space of A. Natural question, how do you find the basis for the column space? How do you find the basis for the null space? Let's work on my example 1, right? So for example 1, without further calculation, I can tell you that the column space of A is the span of column 1, column 2, and column 6, which are respectively 1 minus 2 minus 4. And what'd I do? Oh, 3, 3, 3. And what's the other one? The 6th one, I did what? I did 1, 0, 0. Yeah. How do I know that the pivot columns are linearly independent? What's that?
You took the RREF.
I took the RREF of it, okay. But can you explain to me in terms of the column correspondence property why they're linearly independent? Let me ask a different question, a loaded question. Do you accept that the standard basis is linearly independent? Okay. And a corollary to this theorem would be that a linearly, like if you have a linearly independent subset of columns, then the corresponding subset in any row equivalent matrix will also be linearly independent. To say otherwise violates the CCP. Because to say otherwise is to suppose that there exists a non-trivial linear combination between the vectors that we're talking about, which then by the CCP would transfer back that non-trivial linear combination to the original matrix, violating the assumed linear independence of the original set. So in short, pivot columns are, by the principle of duh, linearly independent, right? E1, E2, E3, linearly independent. Therefore, the corresponding pivot columns, this one, and that one, are likewise linearly independent, right? But more than that, we can also see that it forms a spanning set. I mean, it's obvious here because we're in 3 dimensions, right? Once you get 3 linearly independent vectors in R3, you're done. But imagine we were in a larger context, right? We would still know we're done because all of the other columns can be built from linear combinations of the pivots. So in short, the theorem is this. The basis for the column space of A is formed by the pivot columns. They're necessarily linearly independent. And therefore, we can say a little bit more about the rank. What is the rank actually as it relates to row reduction? It's what? It's the number of pivot columns. Exactly. All right. how about the nullity? I mean, how about the null space, right? So anyway, rank of A is 3 here. Great. So how about the null space of A? If X is an element of the null space of A, then what is X equal to? X is equal to x1, x2, x3, x4, x5, x6, right? Because it's X is multiplying a 3 by 6. It must be a 6-dimensional vector, right? That's the context here. Yeah? Okay. What are the formulas for x1 through x6? Well, here's the deal. We can look at the reducer echelon form, right? And from that, we can read the formulas for every pivot variable as being a dependent variable on the independent non-pivotal variables. So like, just look at the top row, right? The top row gives me like x1. You guys help me out. x1 equals what?
Minus x4 plus x5.
Now, did you take into account to the fact that that equation literally gives me, see, this literally means x1 plus x3 minus x4 plus x5 equals to 0, right? So we have to move it to the we have to move it to the other side. So there's a minus, right? Like I'm solving for x1, so I get minus x3. See, I need a minus x3 here. Maybe you said that, I don't remember. Minus x3, I need glasses. Plus x4, minus x5, okay, great. And how does it go for x2? Minus x3, minus x4, what? Minus 2x5, okay. x3 is, this is going to be really complicated, watch for it. x3. x4 is, it's x4. I mean, if you don't know that, this is a really hard step. If you go looking for an equation to put there, you're in a bad place. x5, what's x5? Is what? Oh, it's just x5? Oh yeah, duh. And x6 is 0. You're like, well, how does that help us? This is a calculation you probably did last semester, but we're bringing it back. So factor out x3, and look what you got. You got minus 1, 1, 0, 0, 0, plus x4 times 1, minus 1, 0, 1, 0, 0, plus x5 times minus 1, 0, oh, my bad, minus 2, 0, 0, 1, 0. Let me give these things names so I don't have to write them again. Let's call this thing V1, let's call this thing V2, let's call this thing V3, all right? Question, can I be confident that these vectors I've just produced, V1, V2, and V3 are linearly independent? What do you think? What's that? You said no? Okay, suppose one of them depends on the other. What would that mean? Keep it simple. What if V2 was like 2 times V3? What would that mean?
V2 is a linear combination of V3.
Yeah.
X is a linear combination of x3 is a linear combination of x4.
That, yeah, I mean, what it ultimately would mean is that x4 and x5 are not independent. If these vectors are actually like scalar multiples of one another, then you can kind of like put them together, and it ends up interlinking the variables. In short, these vectors that we found, they have to be linearly independent, because if you really look at it and search your heart and think about it for a while, you will come to the conclusion that it would force an additional relation between the non-pivotal variables, which is impossible. All right, the non-pivotal variables are free. That is the structure of the solution set. So what I'm telling you is to find the basis for the null space, this is what you do. You look at the reducer echelon form, you write down the solution in vector parametric form as a span, and the vectors which appear in that linear combination, those are the basis for the null space. So like null space here is this of A is the span of V1, V2, and V3. So what's the nullity? The nullity of A is equal to? 3. Okay, everything's 3 here, yeah.
Does this mean that it's not true that the nullity of A and the plus the rank of A is equal to M?
It is not equal to M. What is the nullity?
Necessarily.
Well, what is the nullity of A? Actually, so what is the nullity of A equal to, by the way? Good question. This is equal to the what? Number of free variables. It's the number of free variables in the homogeneous solution, also known as the number of non-pivot columns. What happens if you add the number of pivot columns plus the number of non-pivot columns? How many columns you got? You got 6 here. You got all the columns. You got n. So that's a theorem. This is the so-called rank nullity theorem. It says that if A is in R m by n, then n is equal to the rank of A plus the nullity of A. If you understand this carefully, you can crack probably 50% of the questions that they ask on the subject math GRE.
So, what if you were to just add another vector
What do you mean?
to, if you just added another vector to A, and then it would be 7 by 3.
Oh,
And there's
you mean,
no-
wait, add it where? In what sense?
Like if you were to just make
Oh.
equivalent to that with another vector again.
Yeah, well, if you did that, that would just increase. If I put another vector here, what that's going to do is going to adjoin another free variable to the solution set, and the nullity will expand to 4 instead of 3.
But is there any way that it could be that it could be linearly independent with those 3 you have there?
I'm not sure I understand your question.
I might not agree. That's okay.
So, is there? I need you guys to help me out. One last thing for today. Tell me what A is equal to. Can you guys tell me what it was?
1, 3,
Read me column by column.
1, -2, -4,
Uh huh.
3, 3, 3,
Okay.
4, 1, -1,
Uh huh.
2, 5, 7,
Okay.
7, 4, 2, 1, 0, 0.
All right. So you guys, I think, have all taken taken calculus 3 for the most part, right? So you know what a dot product is. You're familiar with the concept of perpendicular, right? So whenever we have a subspace of oh, I guess I should just mention this. Row space of A, what's that? This is going to be very surprising. It is the span of the rows, all right? So row space of A is a subspace of, the n by 1 by n dimensional vectors, right? Okay, anyway. So that's a space. And you could define something called row A perp. And row A perp would be like, well, let me just use words. It's the, vectors perpendicular to rows of A, all right? I'll try to be more careful about this next time, but I just want to point out the pattern to you guys while we have all this on the board. These vectors in the null space of A, they are by construction perpendicular to the rows of A. If you take the dot product of this with that, or with that, or with that, you should get 0 each time. Now, if you really search your heart and realize what I'm saying to you, you're like, yeah, duh, it solves ax equals to 0, and that's just a stack of 3 dot products, right? So of course it's 0. What is ax equals to 0 here but the dot product of this with the first row for the first component, this with the second row for the second component, this with the third row for the third component? But geometrically, understand what that means. That means you're looking for a basis. You're getting a basis to the space which is perpendicular to the row space. And that's something that's worth exploring, see, because that means we could do stuff like, you know, take a plane in 4 dimensions, and we could find another plane which is perpendicular to that plane using this idea. Things like that. Which, weirdly enough, eventually allows us to solve inconsistent systems through something called the least squares method. I'm probably leaving that for Dr. Skambordis, though, because I think he'll talk to you guys about inner product spaces quite a bit, and that's kind of the natural outgrowth of that. Anyway, that's all I got for today, guys. So I think that pretty well kills off section 4.8 or 4.9, whichever one it was.